So good afternoon, everyone. I have the pleasure of being here and introducing Young Chen for his presentation associated with the celebration of faculty careers. This whole thing started actually associated with the strategic plan for the College of Engineering, and it was called the Faculty Effect 2020 component of that. And it focused on professional development throughout one's entire career. And it also was supposed to help us align our future initiatives and promotion and tenure kind of processes with changing times. So during this time, there was a desire expressed to maybe take a look at what people had been doing. And 7 years after promotion to full professor was decided as the time period, and that's for most of us been quite a bit longer than that, but to actually present a colloquium and then share what they've been doing with their colleagues as well as what their plans are for the future. And so that's what we're here to do today. This has been going on since 2013 when we had a couple of pilots and it was well received, so we've been continuing to do this. So I'd like to give a little bit of background to Dr. Chen. He came here in 2002 and received a PhD in mechanical engineering from Delft University of Technology in the Netherlands back in 1988. His research interests, as all of you here know, actually include indoor environments, and that includes aircraft cabin environments, energy efficient, healthy, and sustainable buildings, and the analysis of their status. He received several awards in his career, including the Distinguished Service Award in 2013 from the International Building Performance Simulation Association, the John Ryberg Gold Medal in 2011 from the Scandinavian Federation of Heating, Ventilating, and Sanitary Engineering Association, and the Willis J. Whitfield Award in 2007 from the Institute of Environmental Sciences and Technology. So for the most interesting part, then I'd like to introduce you to Dr. Chen, and we'll hear what he's been doing and what he plans to do in the future.
Thank you very much, Melba. Good afternoon, everyone. Thank you for coming here during the busy day. And as Melba just mentioned, we should do this every 7 years, and I just count I've been here for 15 years, so I probably should come back to do another one tomorrow. So this is my outline of the talk. I will give a brief overview of my journey. So I grew up in a rural area in southern part of China on the opposite side of Taiwan. And in 1978, I went to Tsinghua University and I received my bachelor degree in 1983. So it's a 5-year program. Then in 1984, with the sponsorship from the Chinese government, I was able to study at the Delft University of Technology. So where I received my master's degree in 85 and PhD in 88. So I still love this place and I still remember that's the window of my office. So I've been there for 4 years. Then within Europe, actually, after I finished my PhD study, I went to ETH Zurich to do my postdoc for 2 years. And then I returned back to the Netherlands working for TNO as a project manager. So TNO is like a national lab, but it's very applied. So it's more or less like a kind of industrial experience to my view. Then in 1995, I went to MIT, so restarted my academic career. So where I served as an assistant professor and associate professor. So then 2002, I moved here to Purdue, the best place on earth. So, during my tenure, I've been working as a visiting professor, affiliated professor, adjunct professor, and honorable professors in different continents, including Asia, Australia, and Europe. So for more than a dozen of times. So why I end up with the building sciences? So when I grew up in a southern part of China. At that time, we lived in less than 1 yuan per day, not $1 per day. That's like a 10 cent per day type of life. So my biggest dream is not to become a farmer. So, but I grew up during the so-called Cultural Revolution. Probably everyone still have a kind of memory if you are sufficiently old like me. So this dream is very difficult to realize. But fortunately, after the Cultural Revolution ended in 1976, so Deng Xiaoping, the then Chinese leader, decided to restart the university. So then I was fortunately admitted to the architectural engineering at the Tsinghua University, the best university in China. So why I selected architectural engineering later because of my father. My father was a supervisor for a local merchandise company for all kind of constructions. So he always bring home a lot of drawings and so on. And for me, I think that was really nice. So that's why I think I should study architectural engineering. But when I went to the university and I found that, yes, I get into architectural engineering, but there was only two choices for me. Either I study architecture or HVAC, and not the civil engineering I have in mind. So for architecture, I never learned how to do drawings. So I don't know how to do anything with architecture. Definitely I'm out. So I have to select HVAC. So it's not a very sexy area, but I found it's fun, for the rest of my life. Then my bachelor degree thesis, I finally selected the building energy simulation. And I made the choice because I think it is mathematically challenging. And that's because I work with the Professor Yi Jian, who is the son of a math professor. So he always teach me how to use different type of math to solve the problems, and that really fascinated me. And now Professor Yi Jian is an academician of the Chinese NAE. So then the question is, how do I end with the building environment? The energy and the environment is more or less like a twin. So in 1970s, we know there's an energy crisis. The gas station in the United States doesn't sell gas. And energy was a big issue, like the energy use in this country, building use about 41% of the primary energy. So at that time, a lot of studies was done for buildings, try to conserve energy. But of course, China, the Cultural Revolution ended in 1976. So our research in China was a little bit late. So even in the early 1980s, when I started to finish my bachelor degree, we were very hot in studying energy. So at that time, I was using kind of a Laplace transform and Fourier transform to solve the heat transfer through buildings. And the other day, when I prepared this lecture, I pulled out my bachelor thesis, and unfortunately, I don't recognize what is written there. So I remember my professor told me, when you forgot all this math, then you become a very famous engineer. Although I'm not a very famous engineer, but definitely I forgot all my math. Okay. So then after my bachelor degree, and then I have the opportunity to study abroad, and I selected the Netherlands because my supervisor there is studying energy simulation in buildings. And he gave me a very interesting problem because this actually is his chamber for studying energy. So don't look at the arrows now. He did have this chamber has two air conditioning systems. One, you supply the air on the top, and then it gets out in the bottom. And the other one, you actually supply the air vertically underneath the window, and then also it gets out on the bottom. So he thought, okay, for this scenario, the airflow will go like that, and for this scenario, the airflow will go like that, and then the energy use will be the same, because this is just dump the energy into the room, so you should get the same energy. But when he measured this result, and then he found, no, they are different. The one use this one say the energy use is 1 kilowatt, and then he measured the another system energy, for this flow energy is only 600 watt. It's a 40% difference. Then he asked me to study why. So I took this one as my master degree thesis. And then at that time, the CFD started emerging. Not very many people use CFD 30 years ago, but I was one of the earlier ones applied to the HVAC system. Of course, in the fluid mechanics, there's already a lot of people using CFD. And I found that for the first scenario, yes, he was right, because we do get this type of air circulation, and the temperature inside was uniform. So he supplied 18 degrees air in, and the exhaust at 23 degrees. So there's a 5-degree difference, okay, between inlet and outlet. Now, in this scenario, he didn't realize that the airflow actually didn't reach it to the top. Airflow goes up and then drops down because of the buoyancy. You supply cold air. So as a result, the lower part temperature was lower, and upper part temperature was higher. And then when you exhaust the air on the bottom here, as you can see, this is only about 21 degrees. So the temperature difference is only 3 degrees. And that's why he said, well, let's use less energy. And it turned out, when I found this result, I was very upset, because let's just say my supervisor did a wrong measurement, so it doesn't mean they're really saving any energy there. So, but my research needed to move forward. But at that time, in the Scandinavian countries, they start to use this displacement ventilation. So where you supply the air actually horizontally in the lower part of the room. And then this is cool and clean air. And then you have the people heat source inside, of course, generate buoyancy. And the polluted air will be exhausted in the top. And this will create a cool and clean air in the lower part. And then, of course, you have warm and dirty air exhaust. Then, if this is applied for heating, that sounds is a great idea. And I said to my supervisor, I said, well, this really looks like what we studied, but just turn this diffuser 90 degrees, and we should be all set. And we can really solve this type of problem, because when you design such a system, there's a lot of risks there. For a designer, you need to understand that there's no drop risk on the bottom, because the cold air might go directly to your feet. And on the other hand, you need to control the temperature certification. If the temperature gradient too big or too small, you might end up very uncomfortable. So this part the CFD can do. And on the other hand, they claim this one can save energy. Look at it in the theory, yes, it's possible, but they needed to calculate that. So with my knowledge in the bachelor degree, I have done energy simulation, and then for my master degree, I've done the CFD simulation. Then I said, look, for CFD simulation, I could really obtain the temperature on the boundary conditions from energy simulation program. On the other hand, the energy simulation program needs the information about the indoor air distribution, which is available from CFD calculation. So if I combine these two programs, and things I can solve a pretty good problem, which forms the basis of my PhD degree. So when I combine them, and of course there's also a lot of challenges there. For example, CFD, your time scale is in terms of a second, and then you solve like in this room, you probably use tens of thousand grid at that time. And then it takes maybe a week in the computer mainframe to do the simulation at that time. Then energy simulation, the heat transfer, the time scale is in terms of hours. And you consider each room just one node, one temperature. And then although the program is very complicated, but you can solve it in seconds. So the combination of the two was pretty challenging. And I don't think I'm going to go through the details. But I finally succeeded in combining these two programs and produced a couple of research papers. And then I wrote a thesis on this title. And a publisher came to visit my supervisor and was interested. So he decided to publish this thesis as a book. So I was very happy. We just decided to print 400 copies, and I earned $1,000 as a loyalty. So maybe today $1,000 doesn't sound very much, but you know, this is 30 years ago. As a student, I was very happy about that. So that's the first time I realized that the knowledge can really sell for money. And that's why I decided to stick it to this field. Then my PhD postdoc, I continue to work on this, and I geared towards more engineering applications. And then finally, I produced a design guideline. This was the second book we produced for ASHRAE for how to design displacement ventilations for different types of spaces. And this book was sold pretty well. ASHRAE informed me a couple of months ago they decided to print the second, to have a second print, and I'm working to revise this book. So this is about my story and with the building science. Now I'd like to highlight a few things about this building environment. You know, later work, my work was focused on building environment. That's because in the 19th century, people only care about any poisoning stuff. Even in the early 20th century, there was a contagious disease across the entire Europe. So you probably learned the H1N1 influenza. That was in 1915, which killed 50 million people in the world. So the indoor environment, I mean, especially thermal comfort, was become popular only in the 1930s. So today, of course, we care more than just thermal comfort about the disease removal. We think about comfort, health, but also productivity and the safety, etc. So if we look at the future, and we'll think more about the personalized environment. Because like in this conference room, we sit close to each other. So if someone was sneezing or coughing next to you, you are likely to get a disease. So we need to design something which will really accommodate the individual's need. And I also look at the clothing level. You know, we have somebody just really in t-shirt and somebody with a very thick jacket. And that means the thermal comfort level in this room might not really fit your needs. You have to use clothes to adjust the needs. So that's why we need to do a better job in design the built environment. And also one thing is to use the CFD approaches. So CFD actually refer to three major steps. One is to solve the Navier-Stokes equation without any approximation. We call this as DNS, direct numerical simulation. And the second one is to solve this equation, but use some type of modeling for the turbulence. And then the final one is RANS, is really solve the turbulence viscosity by using modeling. So these three results actually can be seen on just a velocity scale versus time here. So DNS actually calculate all the details, all the turbulence into a very, very small scale. Now, largely simulation, you only calculate the major fluctuations, of course, which is turbulence. And the RANS model only solve an average velocity and then the percentage of fluctuation. So let's say three different methods. Now, let's say a lot of study been done on this field, but when you apply it to the built environment, then the question for an engineer is which one to choose. So if you look at the history, of course, there's a lot of models being developed for RANS, for LES, and which one to choose. That's not a very easy job for an engineer coming in and pick up whatever is available and do the simulation. And sometimes, in the fluid mechanical area, they of course can combine different models together. For example, you combine two different range models. There's a SSTK omega model, is that kind. Or you combine range model with the LES, it becomes a DES. So my past effort is really try to study different type of models, and then try to find out which one is good for buildings. So we look at a number of different building flows, and then use a different type of models, and then try to grade them and to see which one actually work the best for all type of flow. On the other hand, we also look at the computing cost. For example, if you look at the LES, and of course the cost will be like a couple of 100 times more than the simple model. Then your question is, why do I need this complex model if a simple model can work? And that's actually a lot of engineering choices there. It depends on what type of information we need, and and the design criteria. So I think in the design world, they always needed to have multiple choices for their design purpose. So just to show you how we often use this to do the building mounting study. So this is just to give you a scale, okay? That's 100 meters there. That's a group of buildings together. And this a study did in Japan. They measure the outdoor and the indoor airflow. And especially if you want to design natural ventilation, and you need to do the study. So I used just this 10 buildings to do the study. And this is a photo of the 10 buildings there. And they also measure the airflow inside of one apartment in detail. Now, with the larger simulation, as you can see here, you really can calculate the airflow around the buildings. Okay, so this information is very important if you want to design like a natural ventilation. How much air can come in? And before you do that, you do the outdoor airflow simulation, and you need to make sure this simulation is correct. Because in the CFD application, there's always, not a real joke, people always say like this. If you do the CFD simulation, then nobody believes your result except yourself. And if you do the experimental research for the flow, then everyone believes your result except yourself. Okay, so that's the reality. So we need to validate it. So we use the data from the measurement from Japan. So, but of course, the measurement is very challenging. You really cannot have so many sensors around buildings. They only can measure a few things. For example, in this case, they only measure the pressure around the buildings. So you can calculate the pressure coefficient. So as you can see from this result here, they are not perfect, but it's sufficiently good for engineering application. And then with that, then I can calculate what happens inside the building. So which is really a very good design practice. And then, of course, inside of buildings, you need to compare again what is simulated and what is measured. And because this is a very complex scenario, when you measure inside of buildings, that moment, the boundary condition might not be the same as you use it in the simulation. So you never get the perfect agreement. So I will say that if you get the agreement, something like this, with the magnitude of order the same, and the difference is about 20%, that's very good. But the simulation really takes a couple of weeks for the one I just showed you. So as a design engineer, you definitely have no patience to wait for a couple of weeks in order to do a design case. So my effort in the past few years was try to accelerate this. So I use this fast fluid mechanics. In fact, it also solves the Navier-Stokes equation, but just solve this turn by turn by using the split method. And then finally, you solve this pressure turn by using semi-Lagrangian approach. So this one is being used for the computer games. Of course, for computer games, if you get a reasonable visual effect, you are satisfied. But when you use it for building design, we need for look for accuracy. So with some type of improvement on the FFD, now actually we get a very good agreement, as you can see on the velocity and distribution in these two sections here. So I want to show you how useful this FFD is. For example, if I want to design a room, okay, this is a very simple one, and have an inlet and outlet here. This should be the airflow pattern. So FFD, I can run this up here. So as you can see in this window, you see the air coming in, right? This is pretty fast here. And to show you this is not really animated. For example, if I add a force here, as you can see, there's a lot of things that can be changed. And if I want to study, for example, the smoke inside our buildings, then I can add a smoke here. And you can see this air getting cleaner and cleaner. So with this FFD, the beauty is very fast. With this, my computer here, as you can see, that maybe the font is too small here. This is about 86 times faster than real time. That's why you see the flow goes very fast. So this has been a rather powerful tool for engineering application. But that one, I mean, if you use it for a reasonable size of building, it still will be too slow. And therefore, we try to use different approaches to enhance the speed. So for people like me, when we buy a computer, in the old days, we always look on the CPU speed, look at the frequency, right? And now frequency has been increased to a certain speed. You cannot enhance it anymore because too much heat has been generated in the processors. And now today, like young people, we have quite a few students here, you buy a computer, you look for the graphical cards. Graphical cards, you have multiple processors inside. Each processor is not very fast, but you have hundreds of processors there. So although each processor is not very fast, but so many processors work together, it's much better than a single processor. So we try to build the FFD in the GPU, and that has been pretty good. As you can see here, this is the computing time, and that's the number of numerical grids we use. For buildings, we typically use 1 million to 10 million grids here. So without using a single processor, you probably need like a couple of hours to do a simulation. But with this FFD, you already can reduce like a magnitude orders of the computing effort. And then you use the GPU can reduce another 10 to 30 times further. Depends on the number of grids you use. So that's been pretty amazing speed here. Can have 2 to 3 order of magnitude faster. So we try to promote this. And often I like to use this to tell the student it's important, you get the speed right. Now you do the DNS. Now very few people have tried to do that. You really need a lot of grid to catch the turbulent details, and that need 100,000 years to run a job. So if you start your PhD study today, I don't know when are you going to get your degree. But with the large eddy simulation, it still can be challenging with a very good computer. But when you use this range, now it's possible. A lot of design engineers now are using this range model to solve the problem. And with the FFD, then you can do just, during a coffee break, you should be able to get the result. So this result has been recognized. So in 2002, MIT actually use my result as their telephone directory cover. And one thing is when this very famous building is hide here, that's building 50, that's for the Department of Earth, Atmospheric and Planet Science, that's designed by very famous architect, I.M. Pei. So when the building was designed there, and then they found that if you could open the door and you cannot close it, or you couldn't close it, you cannot open it because the wind pressure was too high. That was very famous there. And later on, they have to put the doors on the four corners. The building looks very strange. Of course, I.M. Pei was a very great architect. He designed a lot of famous buildings, but also have some failed buildings didn't mention here. Now at MIT, there's a development at that time, designed this computer science building, or status building. So that was designed by Frank Gehry, also a very famous architect. So he was afraid of falling the same mistake. Then he asked me to do the simulation on these buildings, make sure there's no similar problem occurs. Well, today the building was there, and there's no bigger wind, although it was in Boston. So it's the proof that in practice, this tool has been not useful. Now, since I moved to Purdue, I changed from the Department of Architecture to Mechanical Engineering. So I found this really give me a new horizon to work on something different. Because at MIT, I work on, with the architect, I have to focus on building. Now, when I moved to Purdue and I look at the airplanes, you know, airplane is a major problem in case of an infectious disease outbreak. You know, we know there's a SARS in 2003 and H1N1 influenza in 2009. Just within a very short period of time, the disease can be spread all over the world. And this is very different from 100 years ago. You know, when the Spanish flu killed 15 million people, that was focused on Europe. You can imagine if the Spanish flu is occurring today, then the entire Earth might be wiped out. So that's the reason it really made me interested in studying the airflow, the infectious disease transmission in the airplane. Now, how the airplane works, maybe some of you might not know this. So airplane, you really get the outdoor air through the engine. So engine do the compression, make the pressure sufficiently high, and then you go through the air conditioning tank, do the air conditioning process, and then you have the right pressure, right temperature, and then send the air into the cabin. And of course, a lot of dirty things occurs in the cabin due to the passengers, and a part of the dirty air needs to be dumped outside, and another part can be refilled and recirculated. So then my job is to look, you know, different type of effect in preventing the infectious disease. For example, we in an airplane, there's always a lot of small nozzles overhead. We call it gaspers. So if you could turn on the gaspers supply very clean air, maybe used to prevent the disease transmission. So, but when we do that, we find it's very challenging. You know, airplane is being manufactured into a very high precision. Even that gasper has only a dimension like 0.1 millimeter in the opening size, or 1 millimeter in opening size. And to simulate the flow from the gasper to the person, we found that we need a 12 million grid. If I do use less than grid for that, and you can see the result, they are different. So that was very challenging. If one person needs 12 million and talk about a plane, you know, I don't talk about the A380 or Boeing 747. The Boeing 737 could house 200 people. So we will need a supercomputer for this study. So on the other hand, the airflow inside of the plane was very challenging to study. Although everything is a steady state, but we find the flow is not stable. You know, this is not just turbulence. It's a low frequency type of oscillation. You can see here, just in different rows, even the boundary condition is the same, the airflow pattern is not the same. So we have to develop a lot of methods, try to simulate the entire airplane. This is an MD-82 airplane with 21 rows. Finally, we can simulate it with the 20 million rate. So this was a pretty challenging problem to study. And then, of course, we, by working with the Tianjin University in China, we could measure what happens in the cabin. And the cabin is pretty big. You know, normally when you use a PIV to do the measurement, you only measure a very small domain. So we could manage it, you know, to combine a few images together, and we get the airflow inside of the cabin. And then we use even a full-scale real airplane to measure the boundary condition. And then we find this boundary condition was just as mad as you can imagine, as messy as you can imagine. Normally we think the airplane, you know, this is really high tech, right? Everything is measured into very high precision, as I said, 1 millimeter for the opening. But we found that when I measure the airflow supply on both sides of the plane, they are not symmetrical. Even along the length, you know, some of them very big flow, some of them very small flow. And later on, we find that even you just have a very small nail hammer into the inlet could change the airflow pattern dramatically. So this is not an easy problem to solve. But anyway, I think by doing very detailed measurement, we were able to get the boundary condition for our simulation. And with the simulation, you can do a lot of fun things here. For example, if I want to study somebody is coughing, like this person is coughing, and then this is a CFD can do. You know, you can really study how the particles with the virus is traveling inside. And of course, this must be a very powerful cough, otherwise it doesn't go 2 rows away. And this only can be done through the CFD. Because with the CFD, you can see all the details, where the airflow, the particle is going, and you can even see the particle size, you know, it's evaporated during the transport. And this type of details, you cannot measure it, because any equipment, so far, we don't have the ability to capture this type of details. Now, when we look at the airplane in reality, try to understand how the SARS occurs. This is a very famous flight from Hong Kong to Beijing in 2003. And that's one person with the SARS stay here. And that's only 2 hours of flight. And later on, they found that about more than 20 people in the cabin was affected, and 4 of them unfortunately died. Now, if you look at this cabin, and then you will see, well, the people affected might not just stay near this person. You know, some of them can be a couple of rows away, 7 or 8 rows away. So we need to understand why it occurs. So we suspected that a walking person could really have an impact. Let's say a person walk around, let's say the impact doesn't just there. But if we stop here, and then you can see the virus really could go to the cabin. And that person could be affected. But of course, this is no proof we can really confirm that's really the true case. But in theory, you know, this is a possible scenario. And with this, I think CNN was getting excited a couple of years ago. They decided to show this to the public. So they used our result to show, you know, how important the transmission can be. So we simulated a case, one person here who is coughing, but this is just a normal cough, okay? You see, it doesn't go very far away. And then by working with the Harvard School of Public Health, we try to understand, you know, if somebody cough out with the SARS or influenza virus, how many people could be affected? So, and that I think I found is very interesting. By working with the public health scientists, they have a model can tell us the possibility someone can be affected by a certain level of a virus. And for this cabin scenario, I just want to show probably, this is just wait for a few seconds, we're going to end. We'll find out those people will be affected with a possibility of more than 90% for a 4 hours flight. So when you are flying, so it's better not to sit with someone in the same row. Okay, sit in the front or the back will be fine, but not in the same row. So this is just to show the importance of the CFD result. But of course, you need to know who is sitting there. And I think that still some of you might remember this person called Andrew Speaker. In the US, we have 2 lists of non-flight lists. One is for terrorists, of course you cannot fly. And another is for someone like Andrew Speaker who has incurable tuberculosis. So that he cannot fly. But this guy wants to marry her, and they decide to have a honeymoon. So as a result, they flew out of Atlanta to Rome, and then returned back to Toronto. Probably some of you still remember the news, right? Then people asking me, CNN asking me, well, can you do something to catch this person in case he was born in an airplane? So, of course, now the sensor doesn't have the ability to detect the TB right away. But suppose if we have a sensor that can detect the TB right away, for example, I install the sensor on top of the ceiling here. And by using the so-called inverse modeling, we could really determine where is the source. So this is just inverse simulation. And we find more or less the area we like to find. And of course, this one, you cannot just solve Navier-Stokes equation to get it, because Navier-Stokes equation is not reversible. When you reverse, it doesn't work. So we have to change the Navier-Stokes equation a little bit to make sure it doesn't really lead to entropy production. So that was also reported by CNN. And now if we think about this reverse simulation, we could think about how about I design something even better. For example, somebody like Melba, you sit there, you want to be comfortable. I only want to design your area or the area in this could be comfortable. And in the front, nobody there, we don't have to take good care of that. So which means I just wanted to see, can I find out what type of a system could lead to that type of design? And lastly, inverse modeling. So traditionally, you can try multiple ways. You might not get a good result. And therefore, we just use this inverse modeling. And in the past few years, we have done a number of inverse modeling, as you can see here. And I want to just pull out just 2 methods. One is a genetic algorithm, which really uses the genetic algorithm method to select the best solution. You could finally end with the best solution, which could lead to the desirable design. For example, for this simple room, and then we find out with the parameters inside of this color domain, which means a certain temperature, velocity, and angle combination, you can design the environment around this person to be comfortable. And the same thing, if I use the adjunct method, which is a kind of gradient method, you can also find out what the best solution can be. So to do this, it can be very interesting. For example, if I want to design a diffuser which can supply the air velocity uniformly through the diffuser, and by using this adjunct method, you can find out a very strange shape of duct. Okay, this duct I don't think you can imagine yourself. But by using inverse modeling adjunct method, they can produce this shape, and then get a very uniform distribution. Otherwise, your conventional design, you will never get that type of uniform distribution. So we use this method In fact, it's really the gradient based. For example, just like you are shooting basketball, first time you shoot it doesn't get in, then you adjust the distance through the gradient. Okay, then the second time you will get it. So with this, I use the method to design the thermal comfort inside of the cabin. Traditional design, you will not get very comfortable result. But the immersion modeling will allow you to get the best comfort possible. But of course, then the diffusion location, the velocity, the temperature will be very different from the traditional approach. So this approach, you will normally cannot imagine yourself. But of course, there's still a lot of things needed to work it out. But with this, we are happy that another publisher, the Tyler and Francis, decided to publish a book on this one. So this book will be published in July. It's 80,000 words, 6 chapters. So, yeah, I use quite a lot of time now. Okay, just quick here. So in my career, I've published 3 books, edited a couple of journals, and then published over 200 journal papers, a few book chapters, etc. Also get some patents, invited to deliver a number of lectures. So just mention here, let's say it's a Google Scholar. Today I just look at over 10,000 citations in my career. And since 2012, I have about 5,000 citations. Melba just mentioned a number of important awards, so I don't think I need to go through the details. So finally, I want to spend just 3 minutes to talk about another aspect that I contribute to, that's about services. So since 2007, I've been the editor-in-chief for this journal. This journal is the oldest in our field, one of the oldest in our field. So it's started publication in 1965. So before me, there was 3 other editors. So in early days, not a lot of publications, but since 1990, the publication just boomed, as you can see here. And under my editorship, we improved a lot on the general impact factor. In early days, it was never higher than 0.5. So since I started this editorship, now currently our impact factor is 3.34. So the journal is ranked 3 out of 269 in the building and construction category, 4 out of 379 in the civil engineering category, or 4 out of 172 in environmental engineering category. So finally, I'd like to thank everyone who has contributed to my work. I don't think the one I just talked so far is just my own contribution. The majority was done by my current and former graduate students. Without them, I think probably my publication so far will be just 10. Okay. Then, of course, there's a lot of funding from the government, and then the journal is working with a lot of editors. So I will stop here and to see if there's any questions from you guys.
Well, what's next?
The question, what is next? Yeah, I think this is a very challenging question, right? I mean, it's very short. Definitely, I think the tools I developed so far has been very useful. And Jimmy and I have been working together, try to get something big for buildings. And I still think the building uses so much energy, and people care so much about the indoor environment. So my focus will definitely in buildings. And I'm really looking forward to work with you again to get some bigger things moving on. And both you and I have been looking for opportunities in this one. And you have done a great job, by having this Center for High Performance Buildings. It's a very nice ground work, and I think we can, based on that, to look for something bigger together.
So
Yes.
I have another question. So as you've come along you started with a real fundamental approach,
Yes.
based on, basic principles. And then in latter years, I think supported by computation and, advances in optimization techniques, it's been supplemented, and you've done even more. So kind of where do you see the next, right now, what is the biggest hurdle to making another breakthrough, and what do you think, the moonshot might be in terms of trying to accomplish something?
Yes. Because this is tape record, so I want to recite your questions here for recording. So the question is, where do I see the next move by looking at the past? Because in the beginning I was doing some more fundamental work, then more moving to the optimization, etc. I think it's a great question. And if you look at the building design, we often need a lot of design tools. In the past few years, the application of BIM, Building Information Modeling, was very hot. And of course, the simulations by using energy program like Energy Plus has been always there. Now, for the indoor environment design, we have been lacking the tools. We have a lot of tools, for example, like Fluent. It's a kind of a computational fluid mechanics tools, but it's too expensive for designer to use. Because the building industry is very fragmented. If you look at design firms, they cannot afford to buy a big computer program just for occasional design. Unless the firm like Boeing, they always use this. So I'm just thinking probably one area I like to develop is really to develop not so expensive tool, not too complicated tools for designers to design better buildings. The accuracy is not like technical, very crucial. This is not like a design of a satellite or rocket, right? The precision is very important. In buildings, the temperature slightly higher, slightly lower, they will not kill a person. But we need to think out of box. Now, our traditional design is always, I have the diffusers here, I have an exhaust there, I need to dump so much energy. The question is, I just want myself to be comfortable in my one-person office. I don't need to condition the entire space to be comfortable. Now, how to realize that to save energy? And I think this is something we don't have a tool for it. And therefore, I think this is probably a direction we like to go.
Maybe they'll have some after we finish.
Yeah.
Thank you, Jan.
All right, thank you so much.